All right, section 8.1 is about inverse variation. As it says at the top, in math, in life really, there are things that vary inversely. This basically means as one value gets bigger, the other must get smaller. Now when we're talking about that in math, our equation is y equals k over x. And like I said, our two variables here are x and y. As one of them gets bigger, the other gets smaller. So as y increases, x decreases. And the opposite is true. As x increases, y decreases. One example that I think about a lot with this is talking about speed, distance, and time. We've kind of touched on this equation before, but speed equals distance over time. That's something you guys have known for quite a while. Something you've seen before in school, different things. Speed, distance, and time. So it follows this same pattern here as y equals k over x. As one of them increases, so speed and time are variables, as speed increases, time will decrease. Also, if speed were to go down, then the time it takes you to get somewhere will go up. So that's one example of things that vary inversely. Now, this whole thing, inverse variation, is in contrast to direct variation. We talked about this earlier in the year. We said direct variation followed this pattern, y equals kx, whereas inverse variation is what we're talking about now, y equals k over x. And both of these, k, remember, stands for the constant, k for constant, right? Direct variation, as one variable goes up, the other goes up. Or, as one variable goes down, the other goes down. Hence the name direct variation. Inverse variation, like we just said earlier, as one goes up, the other goes down. Inverse variation, they are varying inversely. So examples might just look like this. For direct variation, y equals 3x. That's an equation of direct variation. Inverse variation would be y equals 3 over x. Generally with inverse variation, you're going to see one of the variables in the denominator, like we have here with that x. Okay? An example. Is the situation below an example of direct variation or inverse variation? Let's go ahead and read it. Obviously there's a chart there with some things written, but let's go and read the paragraph. As x increases, y decreases. This might be an inverse relationship. A plot confirms that an inverse relationship is possible. Test to see whether x times y is constant. So here's what we're going to do. Inverse variation, we're thinking y equals k over x, right? Well, that should also mean, using this equation, that if we were to rewrite this, I can think of this as y times x equals k. These are the same thing, okay? Just one's rewritten a little differently. And I rewrote it like this so that we can see, all right, your constant value should be the same every single time when you multiply x and y. And that's how we're going to test this here. So in the chart, we've got a whole bunch of x and a whole bunch of y coordinates. And when it asks us to test to see whether it's constant, that's what we're looking for. We're going to do just the y value times the x value and see if it's consistent across the board. So the first one here, x times y, 2 times 15 is 30. 4 times 7.5, that's also 30. 10 times 3, once again, that's 30. And 15 times 2, yeah, 30. So in all of these, our k value is consistent. It is 30 every single time. Okay, and it's written out, the same thing's written out here for us. So in this case, k equals 30. Now sometimes you might be asked to go back and write an equation for this, or model a function for this. If that were the case, we would write it as y equals 30 over x. Because, like I said, our k value is 30, so we're just going to plug that in to the equation. Make sense? Okay, on to page 2. How about this one? So a plot of the point suggests that an inverse relationship is possible. Test to see whether the products of x and y are constant. So again, we want to check, there's inverse variation, we want to check and make sure that the k value is always equal to x times y. So in this first one, your k value is going to be 2 times 10, which is 20. Second one, 4 times 8, 32. 10 times 3 is 30. 15 times 1.5, 22 and a half. Pretty obvious to see here that these k values are not consistent. Okay, again, k for constant, it has to be a constant term. It cannot change. So clearly this is not an example of inverse variation. Okay. Now going down. Let's say you know that a function varies inversely. So you have x and y, you know that x is 4 and y is 6. Okay, I'm going to ask here what function models this situation. So I kind of mentioned that before, that sometimes you have to model the function based on x and y values. So if we know that this varies inversely, we know that's a fact, we know that this is fair game. So I'm going to plug in my x and my y value. So 6 goes in for y, 4 goes in for x. And this is going to allow me to rewrite that equation to solve for k. When I do that, one little step here, 4 times 6 is 24. 24 equals k. Now, that's useful because now I can go back and write my equation. Y equals 24 over x. So there's my function. Now, what does the graph look like? That's what question 2 says. So we can take that function and graph it. Now, like you guys know, I generally like to make those little XY charts when we're graphing these. And we are going to make an XY chart, but I'm going to add a couple extra points on each end of it. So normally I start at -2, I use -1, 0, 1, and 2. I'm going to go a little bit further. We're going to start with -4 and go all the way up to +4. I might need some more room. 3, 4. Okay. So we got a lot more to work with here, and it'll make sense in a second why. You should see, this will help us see the graph take shape of what this looks like. So, when I plug in these values for x, I'm going to get some y values. When I plug in -4 for x, what do I get for y? 24 divided by -4 should give me -6. When I plug in -3 for x, it should get -8. Plug in -2 for x, we should get -12. -1 for x should give us -24. What about when I plug in 0 for x? So we have 24 over 0. When you have a 0 in the denominator, remember that's a problem. That is an undefined function. You cannot divide by 0. Plug it into your calculator and it'll get angry at you. It doesn't work. So that's undefined. I'm just going to leave it like that. When I plug in 1 for x, 24 divided by 1 should be 24. 24 divided by 2 is 12. It should be 8. 24 divided by 4 is 6. So now we've got a bunch of points. Let's go ahead and plot these. The graph's going to be kind of interesting. I'm going to have to adjust my axis here a little bit. I'm going to count by 2's on everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 is going to be somewhere up there. And then the same thing in the negative direction. We'll go by 2's in each direction here. So I got -4, -6. That's my first point. So -4 will be here, and -6 should be right here. So -2, -4, -6. I'll go ahead and write these in. Can't skip out on that. -2, -6, -8. Okay. Next we have -3, -8. So let's do that. -3, -8. -2, -12. -1, -24. It's going to be like way off the page. And you're going to get part of a graph that looks like that. Now there's more to this. Let's go in the positive direction. Obviously 0 is undefined, so we don't graph that. When x is 1, y is 24. So let's do that. 1, 24. When x is 2, y is 12. We have 3 and 8. 4 and 6. Let's go ahead and connect those dots. Okay. What you get here are two different pieces to the graph. Obviously, we have part of it down here in negative land, the other part up here in positive land. This is the general shape for inverse variation graphs. Okay? And obviously, that's going to change based on what the equation exactly entails. But generally, you're going to see this pattern a lot. This kind of thing. That's what we have here. I think when you look at this, you can identify a couple things. First of all, like we said, when x is 0, there is nothing on the graph. It's undefined. That tells us that we have an asymptote there. Remember that term from before? We have an asymptote at this line right here, which is the y-axis. Okay. We also have an asymptote at the x-axis. We'll talk more about those asymptotes later, but remember, in general, asymptotes are lines that the graph approaches but never actually touches. Okay. Cool. Let's go to the last page. This is an example little chart for us. The number of hours it takes to paint a house varies inversely with the number of people working. That should make sense, right? The more people you have working a job, the less time it should take. The less people working a job, the more time it should take. Amazing, right? Let's go and look at this chart. When there's 2 people working, it takes 24 hours. 3 people working 16 hours. 4 people working 12 hours. 5 people working blank hours. Well, let's go ahead and think about inverse variation, right? Y equals k over x. And the number of workers we have, think of that as our x variable, and hours will be our y variable. Okay? So we can develop from this a pattern here. Okay? We should be able to find the k value relatively easily because we know that this varies inversely. So that means k, again, we find by doing x times y. 2 times 24 is 48. 3 times 16 is 48. 4 times 12 is 48. And 5 times something is 48. Good news is, since we know for sure it varies inversely, we can find that something. We can find the y value that goes with 5. All we got to do is 48 divided by 5. We're just going to work backwards here real quick. And that should come out to 9.6. So when there's 5 people working, it should take 9.6 hours. Now, we also established that our k value was 48. So down here we're asking what's the equation? Y equals 48 over x. Again, it's a simple equation like that. Graph. Well, there's some points for us that we can use from that chart. We're going to go ahead and do that. And again, I'm going to count by 2's with everything here. 2, 4, 6, 8, 10, 12, 18, 20, 4. Yeah, it's a little tight, but just count every line up there by 2. And I guess I'll do the same thing in the x direction, even though we don't have nearly as many points. Yeah, 2, 4, 6, 8, 10, 12. That's plenty. And let's go ahead and plot these. When x is 2, y is 24. So 2, 24. It's going to be like way up here. 3 and 16. So 3 and 16. There we go. When x is 4, y is 12. And when x is 5, y is 9.6. Okay. So remember, this is going to follow that inverse variation shape that we talked about on the last page. So this, the positive numbers, are going to follow that. And even though we don't have it on the chart here, there will be a negative side to this graph. Now, as we're talking about real world problems here, like you can't have -5 workers and -12 hours or whatever. Just understand the general shape of this graph follows a positive and a negative piece. Last thing, there is another type of variation called joint variation. Go ahead and underline that, highlight that, box it in, whatever. That's just a key term you're going to see pop up a little bit. I'm not going to talk too much about that today, but just know this. This is when one quantity varies directly with 2 or more quantities. So now, in this joint variation equation, we've added another variable. We have z. You also see x, you also see y. That k value is still there, the constant, right? So joint variation can look like that, where you're multiplying x and y. It could also take the form of this, maybe where you're multiplying by x but dividing by y, or even z equals k over xy. So maybe you're taking that constant and dividing by x and y. Okay? So that's it for 8.1.